Hey, what's going on everybody? This episode we're going to be talking about linked lists. I did just do a video on arrays versus linked lists and some of the differences, but it was just an introduction, so if you want a little bit more substance, that's what this video is going to provide you. So hopefully by the end of this you understand what a linked list is and some of the operations you can do on a linked list. So where do we even get started? A linked list is an example of a data structure. If you're in computer science, this word either excites you or makes you want to go cry yourself to sleep. Probably the second one there. But pretty much a data structure is just an arrangement of data. It's a way to store data. A very common one is a linked list. So with a linked list, you can think of it as a chain where you have some data, and I'm just going to use numbers to begin with, but it could be anything. It could be a string, so it could be people's names, or it could be objects, custom objects, whatever you want to represent here. And these are just going to point to the next element. Now, the beautiful thing here is that this arrow, it doesn't have to be sequential inside of your computer's memory. It can just point to any address in memory. So you don't have to set a certain size at the beginning, and if you want to add elements, you don't have to worry about going beyond that size and either having a memory error or having to create a new array. Like, go watch the arrays video. Basically, if you're working with an array, you get a set size of memory. If you go over, there's two things that can happen. The first thing is you can get a memory error, or it might just work, but it's actually causing issues with other things in your memory. So when you're writing in C and it just explodes and stops working, you're probably doing something like this. The other option is the actual storage of the content is increased. And that's an expensive operation because you actually have to copy the elements over to this new array. And that might all happen behind the scenes. I mean, it's not the end of the world, but it's not really ideal. A linked list is different because these can all be stored anywhere in memory. So if we wanted to add another one, we just point somewhere else and add a new value. No problem. We don't have to worry about going beyond the maximum size because we do not determine that size ahead of time. So that is the first benefit of a linked list. Now, here's a big consequence of a linked list. It's a chain. So if I wanted to grab this element right here, I actually have to start at the beginning, go to the next element, and keep doing that until I get here. That's a very slow operation, and that is something you don't have to worry about with arrays. So with an array, you know the size of the elements, and when you index, it just automatically goes to that position. So it doesn't matter if you're accessing index 10 or you're accessing index 10,000. It's going to be pretty much the same speed because it just goes to that spot and grabs the data. With a linked list, it starts at the beginning. So this one is going to be a whole lot faster than this one here. For an array, you could say retrieving data is complexity O of 1 because if you double the length of the array, it takes just as long as it did before to grab any particular element. When it comes to a linked list, it's O of n, because if you, as an example, doubled that linked list and you tried to grab that last element, it's now going to take twice as long because we doubled the list, we doubled the time it takes. So it's dependent on the length of the list. So if you're wanting to know when you should use a linked list, it's definitely not if you need fast retrieval. This is absolutely horrendous because if you have a very large linked list, the process becomes very, very slow. And that's what we really care about when it comes to data structures, is how well they perform as the size increases. So as the size increases, this becomes very slow. Arrays are very fast for retrieval. But what about inserting data? Well, for a linked list, let's say we wanted to insert something right here. Here's how we would do it. If you consider this pointing to the next node, all we have to do is tell it to point somewhere else. So we can say, yo dude, point to this node instead. And this node has some other value, let's say 12, and we tell it to point to this one here. So although it looks a little funny here, that doesn't really matter because again, remember that these nodes are all scattered throughout your memory and it doesn't matter what location they're at. They're not sequential physically. So to insert a piece of data into a linked list, it's actually very quick. Yes, you might have to find the node to start with here, but once you got this, all you gotta do is tell it to point somewhere else and tell this new thing to point to the next value. For arrays, it's a little bit different because if you add an element in the middle, all those other elements have to be shifted over. So you pretty much have to go all the way through the end of the array. So again, just to review what we just said, this operation of adding a node is very quick if the location of this one is known. Otherwise, it can take some time because you got to iterate through the data following the chain until you get to the location you're looking for. So it depends, but it's not worse than an array. Now, if you want to insert at the very beginning, heck, this is easy. You just create a new box over here and point it to the starting one. There you go. With an array, yuck, because you're gonna put one piece of data at the beginning and all of the other ones have to shift over one, which is a process that has to go through the entire array. I don't know why I keep talking about arrays here because this is not an array versus linked list comparison video. That's what we just did on here. Anyways, this is still very helpful. My wife is snoring, so that's what's going on back there. All right, cool. I think we understand so far. All right, so enough of that array comparison. We're gonna get into how you would actually structure a linked list in code if you were forced to create one from scratch. If you're not forced to create one from scratch and you're just using a library where it's already made, then heck, your life's gonna be easy. But oftentimes, for a class or for whatever purpose, you will want to create one from scratch, even if it's just to build the experience. So to create a linked list, there's two things you need. And I'm going to represent these using classes. If you're in C, you probably use structs, whatever, it doesn't matter, just some sort of container. All right, so you're probably going to have a class for a node, which contains one piece of data. And then you're also going to have a class, which will be the actual linked list. So consider this as a containing class that will contain a node. So here's what it's going to look like. Inside of the node class, I'll draw that out here, we're going to have two main components. We're going to have the data and then some way to reference the next node in the chain. So that would probably be called next. This is a very common way to see this structure. A class called node with two attributes, data and next. For linked list, this is going to be a little bit different. We're going to contain the starting node of the list. So that way we can always have a reference to where the list starts. So you have a start. If you're in a typed language, that's going to be of type node. So basically a pointer to the very first node. Then you're going to have methods or operations to do things with this list. So for example, add, delete, maybe a get method, whatever you need to do that works with the entire list. So anything for one particular node is going to go over here in the node class. Anything to work with the whole list, that's going to go over here. So that's what your class structure is going to look like. Now when you go to create an actual linked list, it probably looks something like this. You're going to create a linked list object. So you can call it whatever the heck you want. Linked list, and heck, you will do this by creating a new linked list. And maybe you'll pass in the first node. So you can pass in a number or you can pass in a node object, whatever structure you want to do. Again, I mentioned this, but if you want the code implementation for this, check out link in the description. So you can create that first node. So right now, this is what our structure looks like. We have a node with the value 5. Now every single node we create has data that's going to contain the 5, and then it also has a next. So we can get a reference to this node here using linked list dot and then grabbing start. Because remember, that's always going to point to that first node. So you would define that in this constructor here. Now to create another node, you would say start dot next and assign this some node. So it could look like this. So we create a new node and assign it to the next attribute of this beginning node. So now we're creating that pointer part to another node. And we can just keep doing that. If we wanted to basically follow down the chain, here's what we would do. We would say linked list dot start dot next. That gets us a node, and then you could actually say dot next again to go to the next node. And if it was a long chain, let's just say it was like a few more here, you could say dot next and then dot next, and then you could create another one by saying dot next and assigning it a new node. So you can see it gets a little funky when you're doing it like this. So more than likely, you're going to create some methods in the linked list class to make your life a whole lot easier. Probably this here, a get method. So in that situation, you wanted to grab this node here, you would say linked list dot get. That's going to be index 0, 1, 2, 3. So that's going to get the node for us. Then all we have to do is say dot next, and we can assign it a new node, pass in some value, whatever it might be. So this works, although it's a little verbose. Obviously that took us like 10 minutes to write. I don't want to do all that. I don't got enough finger muscles to type all that. So let's go through an easier way. Let's talk about using one of these methods, such as add. We can define this such that we pass in an index we want to add at, and then what value we want to put. So we could say we want to add at index 4, so 0, 1, 2, 3, 4. We want to create a new node here, and we want to put some value, let's say 25. So we would just say add, pass in 4, comma, 25. Now, what would the method declaration look like so that this works? So it's probably going to use this get method, which will just iterate through the elements. Once we get to here, we can assign this to a variable. So this is for the declaration. We can say node equals get the position. So that position's passed in here. And then we need to say -1 because we're trying to get the one before it. And then we just say node dot next is a new node, and we pass in the value, which would be 25. So that is an example of how you would implement a method such as add. Let's take a moment to think about what this get method might look like. The way we would invoke it would be like so. We say get, we pass in some index, let's say 4. Well, we always start at the beginning. How do we get that beginning node? You tell me. Oh, good job. We start with start. So we'll just get a reference to that. We'll say node is self.start. The self thing is because we're defining this within this linked list class. So whatever linked list object we're talking about, that's going to be referred to here. That's for Python syntax. If you're in Java or C#, I think it'd just be this, which is implicit, but besides the point. So we get that first node. Then we pretty much need to replace this node with the next one a certain number of times, and that is how you're going to traverse through a linked list. So you create a loop structure. In Python, it would be something like I in range, and then you would pass in the index. So this value 4 would go here inside of these parentheses. I ran out of space, but you would create a variable there. So 4, would be parameterized to go right there. So 4 is that variable, and that's going to be passed into this range. So this loop will happen 4 times in this situation. And each time through the loop, here's what's going to happen. You're just going to grab the next node and replace this variable. So you will say node equals node.next. So this part happens first. So it grabs that next node, so now we're pointing here, and assigns it to node, replacing the original value. So we basically just moved our pointer from here up 1 to here. And we repeat that process 3 more times. The next time node is node.next, we move it here. 1 more time, we move it here. And then 1 more time, we move it here. So now, at the end of this loop, so outside of the loop, node points to this value right here. And that's exactly how you get that value, so all you have to do is say return. You can just return that node, and then whoever invokes this method has a shortcut to get a particular spot in that list. So that is how you would get a value. Now I want to talk about how you would add or delete a value at the beginning, because it's actually a little bit different. So let me clean up a little bit, because this is disgusting. All right, so you have add, delete, get. You have 2 options here. The first one, you could put some casing inside of the add and delete to check if the index is 0, which would be the beginning. Or you could create another set of methods, add beginning and delete beginning. Then inside of that casing, you can just invoke the beginning variations. That's just some decision making if you want your code to be more modular into these individual methods. So let's say we add those methods in here. We'll put add beg because it's long, and delete beg. So these would be invoked if you want to add or delete at the beginning. So how do you get reference to that very first node? That's right, this here. So these methods are going to use this. Methods. So imagine we have this linked list. So far it's pretty, but I'm probably gonna slaughter it in about 2 seconds, but we basically need to add a new node over here on the left. All we gotta do is create a new node, point its next to that original start position, and then replace start to point to this new node we just created. And you can put whatever value you want in there. So to invoke it, it might look like so. You can say add beginning, pass in the value 0, and let's go through the process. We're going to create a new node. We're going to say node.next is equal to the start, and then we're going to replace start to point to this new node. So this is what it would look like. Let's talk about deleting now. We can actually keep that list the same. Let's say we wanted to get rid of that 0 at the beginning. So we invoke delete beginning, and you don't actually have to pass in anything because it already knows the index and you're not adding a value, so you're good to go there. All you gotta do with this is replace start to point to the second element in this list. So we're gonna skip that first element at index 0, go to index 1. So just gonna change that pointer, and that's it. So to do that, all you gotta do is say start is now equal to start.next. So you just move up 1 and replace that value. Boom, you just deleted an element at the beginning. Super simple. Last thing I want to talk about is how to append data. So if you wanted to add a node at the very end, append, and then you just pass in some value like so. Let's see what this definition might look like. You first grab that starting node. So node is the start. And you're going to continue to replace this node to go through the nodes. And you're going to do this in a loop. So while, and we'll just say true to make an indefinite loop. It's just going to keep going until we break out of it. And to check if it's the last node, we just have to see if next is null or none in Python. So while true, then we can check if node.next is null, we're going to break because we got that last node. Then we just define the next of this node. So we just say node.next and assign it a new node. And we'll pass in whatever this value was. We'll parameterize it. It's hard for it to say. We'll just say val, and that is how you would append. And then if this is not met, what we're going to do is just say node is node.next. It's kind of sloppy in there, but basically that's how we progress to the next node. We keep doing that until we get to the end. All right, so that was a ton of information and lots of drawing, lots of explaining, and honestly, this is probably pretty confusing if you don't have the code sample. So what I recommend is go through this and develop a linked list from scratch. Open up Python, I recommend it's very simple syntax, or Java or whatever language you're using, and build a linked list that you can run all these different operations, including append, and it works. Do some tests, try appending, try adding at the beginning, deleting at the beginning, and see if you get any weird occurrences.